We're talking about section 14.6. 10 is not a B or C level problem, but it is rather involved, so I thought I would go over this one with you. So you're given 3 points. You're given A, B, and C. Here they are. And you're given 2 translations. Translation T maps x, y to x plus 3, y minus 1. And translation S maps x, y to x plus 1, y plus 4. So those are translations. And what you need to do is draw the triangle ABC. Well, I left that to your imaginations. And then I have to figure out the image of each one of these points under a composition of mappings. So I have to figure out the image under S composed with T and T composed with S. So that's my job right now. I'm going to start with figuring out the image of these pre-image points, A, B, and C. All right, so what happens here with S composed with T? This means that I have to do translation T first, followed by translation S. Remember, you work from the inside outward. So translation T, it adds 3 to all the x points. So you can see 4 plus 3 is 7, 1 plus 3 is 4, 0 plus 3 is 3. Also, translation T subtracts 1 from all the y coordinates. 1 minus 1 is 0, 5 minus 1 is 4, 1 minus 1 is 0. Okay, now these are the image points of A, B, and C, the pre-image points. Now these points become the points that I apply this translation to, S. So now these become the pre-image, and I got to find like a second set of image points under S. So I do T first, then I use these points here as the pre-image for S, and then these guys are the image points. So you can kind of see it's like taking a trip from LA to San Diego, but I'm going through Irvine first. Okay, so from S, translation S takes point X and it adds 1 to each, not point X, it takes coordinate X and it adds 1 to each X. So here we go. 7 plus 1 is 8, 4 plus 1 is 5, 3 plus 1 is 4. Also, translation S adds 4 to each of the Y coordinates. So 0 plus 4 is 4, 4 plus 4 is 8, 0 plus 4, of course, 4. So now these are the final image points here under this composition of functions, S composed with T. T first, followed by S. There they are. Now I got to do it the other way around. All right? The question says, find the images under S composed with T and T composed with S. So here we go. It's the same process. Okay, so here are my pre-image points. First I apply S, and remember what S does is it adds 1 to the X's. Okay, so you can see that. 4 to 5, 1 to 2, 0 to 1, and it adds 4 to the Y coordinates. 1 to 5, 5 plus 4 is 9, 1 plus 4 is 5. Now, after I've done S, followed by T, so translation T adds 3 to all the X's. 5 plus 3 is 8, 2 plus 3 is 5, 1 plus 3 is 4, and translation T takes 1 away from all the Y's. 5 minus 1 is 4, 9 minus 1 is 8, 5 minus 1 is 4. Now, what I want us to do is take a look at these final image points under T composed, S composed with T, and T composed with S. And what you're going to notice here is that these final image points are the same. Okay, so that is significant. All right, they're the same. In this case, the order that you compose the functions doesn't matter. Frequently, the order will matter. In this case, the order doesn't matter. I could have composed S. I could have done T first and then done S. I could have done S first and then T. All right, that's going to become significant later on in your math careers. All right, so does S composed with T appear to be a translation? Yes, it does, because what it's doing is it's taking 4 to 8. I'm adding 4, S composed with T. All right, I add 4 again. 1 plus 4 is 5. 0 plus 4 is 4. And so I add 4 to the X's. And what do I do to the Y's? I add 3 to the Y's. 1 plus 3 is 4. 5 plus 3 is 8. 1 plus 3 is 4. So it does appear to be a translation, and the translation is this. We said it was x plus 4 and y plus 3. So this composition of functions takes xy to x plus 4, y plus 3. All right, that's part A. Part B says, is S composed with T equal to T composed with S? Yes, we just proved it. Whoop-de-doo. In part C, we want to know S composed with T. It takes point xy to x plus 4, y plus 3. Okay, so we did that. We did that already. And then if you notice with T composed with S, same deal. Okay, we add 4 to all the x's, and we add 3 to all the y's. So you can see that the composition of the functions does the same thing. All right, so that's problem 10. It's a little involved. Okay, now problems 13 through 16, we have to tell which of the following properties are invariant under the given transformation. Okay, the properties are distance, angle measure, area, and orientation. All right, so I'm going to make a little list of all the properties here. Distance, angle measure, area, and orientation. Okay, so we're going to look at each of these mappings and see what we're dealing with here. Okay, so the question for 13 says you're given a composition of a reflection and a dilation. So a reflection is an isometry. Okay, it maps a congruent figure to a congruent figure, but a dilation is not an isometry. Remember, that's a similarity mapping. So the composition isn't going to be an isometry. So only angle measure will be preserved, and that's the only thing that's invariant. Okay, a reflection also doesn't preserve orientation. Remember, when you look in a mirror, you don't see yourself quite looking back at you. It's a mirror image of yourself. That's why we call it that. Okay, so a reflection doesn't preserve orientation. So that is 13. 14, if you're composing two reflections together. All right, so two reflections, you're composing an isometry with another isometry. So we did have a theorem, I think it was a theorem, that said when you compose two isometries, you get a isometry. So that means angle measure, distance, and area are going to be preserved, and orientation is going to be preserved under two reflections. You'll reflect it one way, you'll get the mirror image, and you'll reflect it back. You'll end up in the same place. All right. So the first reflection, will take you from clockwise to counterclockwise. The second one will go from counterclockwise back to clockwise, or vice versa. All right. So that's how the two reflections work. The problem number 15. Oh, guess what? I think I wasn't on. I think you heard a lot of talk and didn't see much writing there. Okay, 15. Sorry about that. The composition of a rotation and a translation. So again, we're trying to figure out what's preserved: distance, angle measure, area, or orientation. So a rotation is an isometry, and a translation is also an isometry. So two isometries composed together, the composition of those two will be an isometry. Since we're not dealing with reflections, we don't have to worry about orientation either. So all four of those things, distance, angle measure, area, and orientation, are going to be preserved. And the last problem, I hope you're getting the hang of these. The last problem, the composition of two dilations. So again, dilations are similarity mappings. They are not isometries. So the composition of the two dilations won't be an isometry. And the composition is going to preserve angle measure, possibly orientation. So that's as much as I'm going to say on that. If I have inverse functions, that's too big of an explanation. Forget I even started down that road. Okay, I'm done with this.